Good morning, everyone. Thanks for attending my presentation. The title of my presentation is Shakedown Analysis of Flexible Pavement, Considering Dynamic Effects of Traffic Loading. I will go through my presentation in the following steps. The first one is background, and then I will introduce our research methodology. A computational model will be applied based on our methodology, and then we will discuss the results. Finally, is our conclusions. Pavement design is of vital importance to society and economy. Routing failure can reduce the lifespan of pavements in the long run. The failure of these pavements shown in these two figures is caused by the routing. So, what are the current pavement design methods in US? There are two popular methods. The one is empirical method. The other one is mechanistic empirical method. In the first method, empirical one, all of the data are obtained based on experimentation, so that the relationship between inputs and outcomes is lack of concept of mechanics. Compared with the first empirical method, the second method, mechanistic empirical method, has its own advantage because this method involves the mechanical response of pavement under loads, but the failure state of pavement is still considered and described by empirical method. Though these two methods have their own advantages and widely used, their drawback is that the empirical method is used to describe the failure state, and the results can be influenced by many factors like equipment, environment, etc. To overcome this drawback, we use the shakedown analysis in our research, which is which failure state can be expressed by a mathematical model. And we will also consider the pavement roughness and the response of dynamic loads. Thus, there are three steps in our research. The first one is advanced vehicle load coupling model. After obtaining the amplifier of load, stress and displacement fields can be obtained, and the shakedown analysis can be done in the second steps here. Finally, we will develop a pavement model based on the two previous steps. So, how to obtain strength and displacement fields in a layered pavement system? Here, we use these two elastic equations and using the Fourier transform to solve these two PDEs. Here, these six equations shows the relationship between the original function ft, fx, or fy, and the ones in the Fourier transform domain. So using these relationships, the displacement components and the stress components can be expressed, and in the Fourier transform domain can be expressed as follows. And there are 6 unknown coefficients, and rewrite these equations in a matrix form, just shows here, as here. And combined with the boundary conditions and the continuous conditions, all of the unknown coefficients can be solved. And then we will use the inverse Fourier transform method to obtain the stress and the displacement fields in the physical domain. Okay, as we know, we just talk about how to obtain the how to obtain the stress fields in a layered soil system. We can move to shakedown analysis now. If the total stress field, including elastic stress and the residual stress fields, which is caused by the repeated load, doesn't violate the yield condition, the shakedown will happen. And in this way, the critical vehicle loading is referred as to its shakedown limit, and here we use lambda prime SD to represent it. In shakedown analysis, the most important thing is that under the shakedown limit, the pavement soil system will adapt itself to the repeated load, and there won't accumulate further excessive rocking for the following dynamic load. So as we just talk about the advantage of shakedown analysis, because the failure criterion can be expressed in a mathematical form, just like the equation F shows here. And in our research, we use the Moore-Coulomb failure criterion. And in this equation, we can see here the sigma XXR represents the normal residual stress on the moving direction. M and N are two parameters which are related to shakedown limit, lambda prime, and the elastic stress, which is induced by the moving load. And combined with constraint conditions, we have three here, necessary conditions, yield 1 and the equilibrium 1. We can obtain the shakedown limit for each layer, lambda I prime. And the minimum of them is the shakedown limit for the pavement soil system. Okay, now, as we just talked about how to obtain the stress and the displacement fields in a layered pavement soil system, and we also know what a shakedown it is. So we will use a simplified computational model to obtain, based on the shakedown analysis, and to obtain the shakedown limit. Here in the figure 1, we can see that we have this is it's a two-layer computational model. The first layer represents the pavement, and the second layer is it represents the subsoil, which is semi-infinite. A blue car here is moving on the ground surface along with the positive of x direction. All of the materials parameters which we use in our model are shown in this table. We can see Young's modulus, E, Poisson's ratio, density, cohesion, and also the internal friction angles. Okay, now let's talk about the results. The first is the influence of the friction angles. Here in this result, we fix the E1 over E2, which means the Young's modular ratio at 0.1. The friction angles of the two layers are the same, and the velocities of the moving load is 22.22 meters per second. In this chart, we can find that the shakedown limit, lambda SD prime, goes up with the increasing of the friction angle. And at a given friction angle, for example, let phi equals to 20, shakedown limit grows with the increasing of the cohesion ratio. We can see here, right? Okay, and compared to these four lines, we can also find that the slope of each line also increases with the increasing of the cohesion ratio. Okay, now let's talk about the influence of Young's modulus at various strength ratio. Two charts are obtained at different velocities. One is 40 meters per second, and the other one is 90 meters per second. In these results, the phi one, which means the friction angle for the pavement, is 45 degrees, and the one for the subsoil is 20 degrees here. The cohesion strength for the subsoil is 10 kilopascal. When the moving speed is 40 meters per second, as shown in the left chart, we can see that the shakedown limit decreases with the rising of the Young's model ratio at a relatively low cohesion ratio, just like the C1 or C2 equals to 1 or 2 shows here. However, the shakedown limit goes up first and then goes down at a relatively high cohesion ratio. But if the velocity increases to 90 meters per second, shakedown limit named prime SD increases first and then decreases no matter what the value of the cohesion ratio we choose here. And we can also see another thing from these two charts. At a given cohesion ratio, we can always find an optimum Young's model ratio that provides the maximum shakedown limit. Okay, for example, if we fix the cohesion ratio C1 over C2 equals to 5 and the velocity of the moving load is 40 meters per second, yeah, this line, and we can find that the optimum Young's model ratio is 5 because the shakedown limit is the maximum at this point on this line. Okay, now let's talk about the influence of the Young's modulus at various friction angles. Here the cohesion of for the two layers are the same, which is 10 kilopascal, and the friction angle for the subsoil Phi 2 is 20 degrees here. When the velocity of the moving load is 40 meters degree, we can find that shakedown limit goes down with the rising of the increase of with the increasing of the Young's model ratio. But when the moving load increases to 90 meters per second, it goes up first and then goes down, no matter what the value of the friction angle of the pavement shown here. Here is the influence of the velocities. And there are two charts. The first, the left one shows the shakedown limit at various cohesion ratio. And the right one shows the shakedown limit at a different friction angle of the pavement. We can find that the shakedown limit declines with the increasing of the velocity, which means the higher velocity, for example, higher velocity here, the lower shakedown limit we can get. Okay, here is our conclusions. The shakedown, firstly, the shakedown limit increases with the increasing of the friction angle and also the cohesion ratio. The pace of increase accelerates with the increase of cohesion ratio C1 over C2 here. Secondly, the influence of Young's modular ratio E1 over E2 to shakedown limit varies with the various cohesion ratio as well as the friction angle of the pavement. Thirdly, the larger the velocity of the moving load, the smaller the predicted shakedown limit. Finally, at a given cohesion ratio or friction angle of pavement, it always exists an optimum Young's modular ratio that provides the maximum shakedown limit. This research is supported by Tran-SET, so all of our authors wish to thank their supporting. At last, thank you for you all to attend my presentation. Any questions?
Thank you very much for the excellent presentation too. Please, if anyone has any questions, we have about 5 minutes for questions. Anyone? Last chance to ask a question. Okay, yes.
I've got a question. As the velocity increased, you showed that that limit decreased. But the problem is normally with viscoelastic materials, when the loading is occurring faster, the material is stronger. Why do you think this is?
I'm sorry, sir. I'm sorry, Doctor. Could you please repeat your questions?
Question was about the shakedown limit decreasing when the velocity is increasing.
Yeah, just like the slide shows here, right?
Yeah, because it made me wonder, because when you have a viscoelastic material like pavement or soil, when it's loaded quicker, when it's faster, normally it has a greater strength. And so wouldn't you think that would increase the shakedown limit? That's the only question. That's my question.
Yeah. So doctor, you mean it also depends. I mean, you mean the shakedown limit also depends on the properties of the materials, right?
Yeah, and I can see what you're talking about here, because you've assumed that the C, the cohesion, is constant, whereas at a greater velocities, it could be actually increased during this. Yeah, I see. That's the reason why, because you've set it as a constant in this particular.
Oh, yeah. Sorry, I forgot to.
That's what it is.
Yeah, this is because I control the C2 when I change the cohesion ratio. Sorry,
Okay.
sir. Sorry, doctor. Yeah.
Okay, thank you.
Thank you, doctor.
And also, I think his solution is based on the plasticity theory, not the viscoelasticity model.
Oh.
Maybe this explains, some of the results.
Okay, got it, Dr. Chen.
Okay. Does anyone has an additional question or comment for Zhu? Okay. Thank you very much, Zhu, for your presentation.